Can a balloon carry it? Can it measure at whatever temperature the atmosphere throws at you? Yes and yes? Good. Let's go. Hi, my name is Alex. I've argued enough for a lifetime. Put your headphones on, sit back, relax, and enjoy your commute or whatever else you're really doing right now. Good night to those of you who use my content to fall asleep. In addition, please share and like or give a thumbs up or do whatever one does on the platform you use to consume content like this. Doing so will help me a lot. Thank you. It is an experiment. Your experiment. Imagine being a scientist on a budget. You need a vehicle which can transport your instruments up into the air. You could build towers, fly airplanes, or even launch rockets. Or you could fill a balloon with hydrogen and let it go. See, when you have finally gotten your research grant, you'll find that it doesn't really amount to much money. So you have to get as much as possible out of it. In this case, that means getting good and useful data, showing you intriguing stuff. The tower may be cheap. Think of a glorified scaffold when I say tower. And it will be there and be accessible for a much longer time than your grant money. Yet it will stay on the spot and, crucially, will only carry your instruments so high. 100 meters or so. Radars and lasers stay on the spot too. Run and run and run and collect data at more or less whatever altitude for as long as you take care of them. But they have issues with respect to how accurately they can measure. Airplanes and rockets may move to higher altitudes, especially rockets do, but the aerodynamics around them is complicated, plus they land rather shortly after they have taken off, so there won't be too much data. They're usually quite expensive too. Of course, what you actually want to do will determine what your options are to begin with. We launched rockets, for example, because nothing else reached the so-called mesosphere. Yet, generally speaking, balloon-borne measurements may very often be your best deal, and probably by a long shot too. Let's set the table to start with. The first record of balloons being used as such goes back to ancient China. There's no surprise there. Those guys were either good at invention or good at writing stuff down. Most likely, they were good at both. These ancient balloons were lanterns called Kongming, or sky lanterns. They were little candles under pieces of cloth. They were minuscule hot air balloons, in other words. They were used during a festival, I think, or maybe they were military equipment. Who knows with history? At any rate, we do know they've been in use for a couple of millennia. And there are festivals in China today, the Mid-Autumn Festival and the Lantern Festival, during which Kongming lanterns are centerpieces. People dangled under balloons for the first time in Portugal, where some Brazilian priests lived in the 19th century. One of them thought it was a good idea to ape after birds by basically building a bird-shaped boat. Imagine Galadriel's swan-like vessel in the Lord of the Rings trilogy, and then arranging the sails in that boat horizontally, such that one could put a fire underneath and help the thing fall at a lot slower rate than it otherwise would have. And that's the best way to put it too, since the contraption, according to legend, was released from some high place in Lisbon and floated down to the ocean like the weird thing that it was. Ballooning this wasn't, but it showed what was to come. In 1783, the brothers Montgolfier conducted the first balloon flight. You probably knew that. It's a famous piece of history. Did you know, though, that none of the brothers took part in the flight? They paid an army officer to take the risk for them. In addition, human beings being what and who they are, it took only 2 years and until 1785 for the first balloon explosion to happen in Ireland, in the town of Tullamore, which was raised by the fires following the explosion. Yes, therein lies a joke, which I won't make. You're more than capable of having made it yourself already. Because I said explosion. How could a hot air balloon even explode? Isn't that rubber or sheet just going to melt or catch fire or something when things get too hot? Yes, but see what these Irish whiskey connoisseurs thought up. was a contraption which was, in principle, much more effective than a hot air balloon. It contained hydrogen. And that's both good and bad. Hydrogen is the lightest gas, period. I'm not happy to say it like this, to be honest, but you probably know what I mean. If you contain a volume of hydrogen in some way and then put it into air, it will float upwards, if it has the same pressure as the air around it. Nothing will be better at that than hydrogen. Also, period. Unfortunately, hydrogen also burns. If you combine it with oxygen, you get H2O, water, which is one of the most stable molecules in existence. So the chemical reaction to get there is powerful. In one word, you know that if you know about the Hindenburg Zeppelin. Zeppelins of the lead and other varieties aren't balloons, although, their whole shtick is based on the same physical explanation. Balloon or airship, though, the basis for it all is called the Archimedes principle. Archimedes. With him, it was all about crowns underwater, in liquid, not in gas, and running naked through Greek towns yelling stuff. Turns out his principle of updraft is true no matter the aggregate state of the matter. Well, it isn't valid for solids for obvious reasons, but the moment matter can move around, Archimedes was right. And yes, the link to Archimedes' ideas is down there in the description. Wait a minute, isn't there also helium? Can't we use that? We could use helium, yes, but that's heavier than hydrogen and more expensive by an extraordinary margin. So we use it, but we use it only under special circumstances, say in a small weather balloon released by school children or something like that. Usually, and in science, hydrogen it is. Moving on. Scientific balloons in themselves are quite cool, not so small pieces of engineering, with the added bonus that it's easy to understand just why they are cool, not so small pieces of engineering. And the experiments carried by them, well, the sky's the limit, as it were. In addition, one can release a balloon from basically anywhere. Not from inside a volcano or in a densely populated area or something like that, but, well, you know what I mean. They're about as safe as it gets. If you can make sure they don't explode and or don't lose their ton-heavy payload, then you're fine. At the very least, you don't take an intercontinental missile, call it a sounding rocket, and launch, quote-unquote, it. What was that all about? Oh, I've worked at that place up in northern Norway where they have launched sounding rockets for over 60 years now. Before I worked there, I was part of rocket science projects at the then University of Tromsø, buying parts of outdated intercontinental missiles, putting those parts together in whatever way seemed most fitting for the task at hand, making a point of not putting warheads but scientific instrumentation in them, and launching them into the mesosphere. But I digress. Think about the following simple question, for example. How high can a balloon go? A little more than 50 kilometers, so a little bit into the mesosphere. Okay. Next question. How would you maximize the height your balloon can go to in order to get there? Now we're talking. What determines the maximum height of flight for a balloon? Its weight. Heavier things don't go up as high. Thank you. What more is there to it? Well, here let me tell you. The second thing which, once thought about, isn't that much less obvious is the temperature. We all know that cold things contract and warm things expand, don't we? We do. With balloons, this becomes a quite distinct, even poignant effect. If your balloon stays up during a whole day, which most larger scientific balloons will do unless you don't want them to, then they will want to sink during the night, when the air is colder and the gas in the balloon contracts to make it smaller. During the day, the effect will be exactly opposite. I'll come back to that in a second. With respect to what altitude a balloon can reach, though, it would be better to have colder temperatures. The balloon doesn't expand as much and won't pop quite as quickly. There are other more subtle things too, like for example the ascension velocity of a balloon, that is, how fast it rises in the air. See, you can control that velocity by the amount of hydrogen you put into the balloon. By the way, if you're wondering, hot air balloons aren't your best bet to get really high. You'll have to fill it with gas and almost close it off. Where was I? Oh yes, high altitude balloons. If you put a lot of gas in them, they will rise fast, but they will also pop at a lower height, simply because, the material will be under maximum stress at a higher outside pressure. So putting as little gas as possible into the balloon will help. Then there's wind. The more wind there is, the lower the balloon will go, even given that its material will be able to withstand mechanical pressures connected to gusts and things like that. So why does a nice and smooth constant high wind not help a balloon go higher? Bernoulli, that's why. Where the wind is high, the static pressure is low. Wind may lead to low pressure at lower altitudes, which will make your balloon expand more than it otherwise would. Now granted, usually a balloon would simply rise through a high wind, entering it from below and simply leaving it above some time later, after which we are back to normal. But in its worst case scenario, winds can make balloons pop earlier. Then there's the effect of humidity, which I've never really understood, to be honest. Once you get out of the troposphere, there simply isn't all that much water in the air. I don't know. Look it up if you must. I'll just move on to something which does intrigue me just a tad more. I mean, doesn't that balloon itself weigh something too? If you really wanted to get high, in that sense, what could you do to your balloon? Make it out of thin material. Okay, doesn't that just mean that it would pop earlier and at lower heights? Of course, it would, but what if we open it up, say, below? Put hydrogen in it, then open it up below. The gas wouldn't escape and pressure could even out inside and outside the balloon, thus reducing the stress on the material. Great thought. That's exactly what they do too. But then again there's a problem. The shape of the balloon. You can't just make it a ball and then poke a hole in the center. That would lead to gas being pushed out until the pressure inside was the same as outside, yes. But the balloon itself would deform. It would become half a ball and a cone under that half ball. Or something similar at least. There would also be, quite obviously, a transition between the two geometrical shapes. In this transition region, there will almost certainly be a different pressure than in the rest of the balloon. In fact, there will be a pressure difference between that region inside the balloon and the outside. The rest is common sense. In order to make the balloon light, we would like to use as little material as possible, yet if the pressures inside and outside are not properly aligned, if there is only one region of pressure differences, then this region will be the weak point of the endeavor, and we will have to design the whole balloon around it. We don't want that, and we don't have to either. There is something called the ideal balloon shape, quote unquote. It's a thing, look it up. It minimizes the pressure difference in that transition region between ball and cone to a point where we can do this. We can build balloons which in flight become several 100 meters in diameter, but consist of plastic a couple of times thinner than a sheet of paper. Go back those 5 seconds or whatever your app allows you to listen to that sentence again and soak it up. If you've been too lazy to click that button, or if you escaped the time loop my order has created, then I will read it out for you once more. We can build balloons which in flight become several 100 meters in diameter, but consist of plastic a couple of times thinner than a sheet of paper. Yeah. Oh, and these balloons, zero-pressure balloons as they are called, can reach heights of more than 50 kilometers above ground too. That's right through the stratosphere and into the mesosphere, that is. Mostly, we're not interested in getting that high. We would like to get to and stay at a particular height, say for example at 30 kilometers, in order to measure the density of something there, and that creates a different challenge, tackling day and night. By the way, don't you just love the banality of these things? No supersonic aerodynamics. Nope, tackle day and night and you're good. So what's the problem, and what's the solution? As mentioned before, the problem is one of contraction and expansion. Warm stuff expands, cool stuff contracts. ask any man about the center of their feelings, or don't. With a zero pressure balloon, this is quite the pronounced effect. During the day, it expands and may hover a couple of kilometers above its intended altitude. During night, it contracts and may hover a couple of kilometers below its intended altitude. To scientists who may wish to make measurements at a particular altitude above ground, this just doesn't cut it. So zero pressure balloons carry extra weight which can be released during night and possess a valve at the top to release gas during the day. In this way they can maintain their altitude quite well. Then of course you have another problem. You can only play this game until there either is no more gas in the balloon or there is no more extra weight to drop. Bugger. 3 days as a rule of thumb. 3 days such a balloon can stay up there. Compared to the couple of seconds of supersonic data a rocket will give you, that's already awesome. Besides, zero pressure balloon, quote unquote. Does that make sense? No, but that's the name given to these things. What is zero is the pressure difference between outside and inside the balloon. Well, it isn't quite either, but you know what I mean. Anyway, zero pressure balloons are used only where measurements need to be made at higher altitudes than around 20 kilometers. For everything else, we can build the perfect balloon. Well, the almost perfect balloon, that is. Hear me out. What if you didn't care about the balloon being heavier? I mean, once it reaches 20 kilometers, then your instruments could already measure lots of stuff, like ozone densities, wind speeds and vortices and so forth. I've got a piece on the Earth's atmosphere to tell you more about the and so forth, and why it's cool stuff. Turns out you can make the plastic of your balloon so thick that you can close it off and have more pressure inside than on the outside once it's up there. So-called super pressure balloons are just that. Since they are closed, there is no exchange of gas with the outside either. The shape and size of the balloon stays as constant as it can be. And because of that, the balloon can stay at around the same height until the material gives out. It does that at the end too, yet there is no need for ballast or a valve or anything. It's just a ball of gas floating up there until the plastic breaks. Mostly until the operators decide that enough is enough, to be honest. NASA once decided not to decide something like that at all. The respective balloons stayed up there, measuring stuff for close to 60 days, if I don't misremember correctly. How cool is that, huh? From a scientist's perspective, I mean. A tenth or so of the cost of those intercontinental sounding rockets that I've mentioned before, and immeasurably more data to build your research on. Check out a French campaign called Concordiasi to know what I mean. The link's below. Now, before you, as in you the rocket scientists, like my former colleagues are, crucify me, no, balloons aren't always what you want to carry your instruments. I've indicated as much a little earlier in this piece. Balloons can't be steered, say along one of the Earth's magnetic field lines for instance, so give it a rest. Nothing's perfect, and as I have said, the starting point is always what you want to actually do. Still, look at weather balloons. They're small, I mean like really small, 1.5 meters in diameter or so at release, and maybe 10 meters or so when they eventually pop. And with them you even forget about the requirement of staying at the same height for an extended period of time. You simply put hydrogen into a plastic, balloon, tie it off and release the balloon with its instruments into the air, like a super pressure balloon. No, not quite. The plastic isn't quite as thick and rigid. It's maximized for price and sustainability. Yes, sustainability. What you'll usually get is half an hour of measurements about the weather. You know, temperature, humidities, radiation, measurements of stuff like that. And that's it. You won't even retrieve anything. The balloon will simply pop and then fall down. It's a small enough affair once popped that there is just about no significant environmental footprint at the end either. About $10 to $100 a balloon. Yet the data acquired helps with some of the most important stuff we do, predicting the weather and understanding climate. There are more than 800 stations around the world which release a weather balloon twice a day at basically the same time and make these measurements. That's nice in itself, but there's more to it too. Part of what makes the weather so difficult to predict is that the whole relevant physical system includes everything, like the whole atmosphere and the oceans and even the constituents of the land masses and how they are distributed around the globe. Everything. Air is the lightest part of that physical system. It is the part that moves around most easily. It reacts to how warm the land is, how warm the water is, and thus also how the water flows around in the world's oceans. Looking at how the air moves around is a job for satellites and weather balloons. See, by synchronizing the time at which the balloons are released, one gets a snapshot of what's happening at that particular point in time, globally. The term to search for is transport models, by the way. They describe how the global winds look like and how they in turn affect the rest of that physical system, by for example making a particular part of the world dry or wet, thus changing the vegetation at that place, thus changing how much of the sun's energy is reflected or stored at that place. For example, think about the Amazon. It gets its nutrients in the form of dust which is blown over the Atlantic from Africa. That's for those of you who ever wondered how fertile the soil in that most humongous of wetlands can really be. You know, like, doesn't a river take all the good soil with it? It does, but not to worry. ... Weather balloons contribute to understanding processes like that. Kinda cool, huh? And all that with the help of a piece of rubber, some hydrogen, and what's called a radiosonde, which radios its measurements back to ground in real time. The luxury of simplicity. Speaking of radiosondes, you can make those as complicated as you want, and people do, for as long as what you end up with is light enough to be borne by a balloon and tackles a minimum temperature of minus 90 degrees Celsius. That's it. There are no other requirements, really. As I said, make the thing as complex as you want. You know what? Let's just take some examples of such radiosondes, shall we? In meteorology, most commonly used one of these is called a PTU sonde. The letters stand for pressure, temperature, and humidity. I know, bear with me. Usually there's a GPS receiver on board too, such that you get 4 different measurements, and with these 4 different measurements, you can do stuff, like stuff, but with a capital S. Here goes. You can measure pressure, temperature, humidity. Okay, sorry, I couldn't resist. Because it's true, you can measure these things. They are fundamental stuff though, which means you can then calculate the dew point temperature, that is, the temperature at which water vapor would become raindrops. The refractive index, which gives you an indication of what air does to light traveling through it. The speed of sound, which does change with height. The air density, the water vapor pressure, the wind speed, the wind direction, and the geometric height, whatever that is, and a few quantum things too. Yeah, that's it. A little box sent into the atmosphere at a cost of literally $100 gives you all of this in real time, because let's face it, the computer calculating all of it doesn't need to be big. These are not like many of the other equations I go on about. These are straightforward calculations, not coupled differential equations. That's true even for the quantum stuff, strangely. Truth be told, the heaviest thing on a PTU sonde is usually the battery. The rest is a simple small circuit card, and that's it. Well, there's an antenna too, but that's just a piece of wire on these sorts of sondes. And of course you have your PC on ground doing the calculations. Another example would be what is called an electrochemical concentration cell. The idea here is based on electrolysis. An often used one of these would contain potassium iodide solution in 2 different, cells into which one sticks platinum meshes. So what's happening? Electrolytic solutions are solutions in which whatever you put in isn't just there but splits up into ions. In this case, potassium and iodide ions. If you have 2 containers and you have different amounts of electrolytic solution in these 2 containers, you can put a wire between them and find that there is a voltage and a current between them. And then you realize that potassium iodide reacts with ozone in quite a predictable way, producing exactly 2 electrons per ozone molecule, I think it was. and you can check that current and how it changes while the two containers float around in the atmosphere. No battery, no nothing, just two containers of potassium iodide measuring ozone for you as the balloon rises. Simple and still kinda cool, huh? Before you say anything, the transmitter does need a battery, but that battery will be smaller than for other probes. Thus, the radio sonde will be lighter, which per definition is a good thing for any balloon payload. You can use that weight for other stuff, or just not use it at all and make the balloon go higher. Now, we talked about winds before in this piece, and the truth is, a GPS receiver tracking the balloon's position in time and space, as it were, can account for a lot of things, because that's how the PTU sonde finds wind velocities. It registers the position once, starts counting the time until it does so again, and looks at how far and in which direction the balloon has moved. But what if you wanted to measure smaller scale air movements, like really small movements, gusts in the nook of a cloud or whatever? Don't shoot me if you're a meteorologist for using this example. The point is, there are small-scale air movements, turbulence often enough in fact. What do you do if you want to measure this from under a balloon? Use a magnetometer of all things. And why not? We do, after all, know rather precisely how the Earth's magnetic field looks. So we can build a turbulence sensor with the help of several magnetometers. The way it works is rather ingenious, to tell you the truth, and it takes into account that the sonde moves under the balloon. It does so in a regular fashion, not quite circular, but rather following an oval-shaped trajectory. It can be your homework to figure out why, and at any rate one can use magnetometers to measure the movements of the sonde itself, and then use statistics to see what would be the norm, the oval that is, and see what comes on top of that, the deviation, if you will. That deviation has to be induced by something else, and we assume small-scale turbulence to be the perpetrator. If this sounds a little iffy to you, then you'd have well-working nonsense sensors, because there's a lot more to the setup, to separating what is wind and what isn't. It involves calibrations with respect to laser measurements and a few other things. But you get the gist. Ingenuity in engineering, and a ball of gas floating up there. That's kinda cool, right? And I can continue too. There's something called a radix sonde. It measures radioactivity, so it's really just a Geiger counter. Which makes me ask the question of whether you really know what a Geiger counter actually is. Do you? Growing up closer to a nuclear power plant than I would have wanted to, I heard about it so often that I never really realized that I didn't know how it worked until I started doing science communication and got asked the question. It's basically a tube with a non-reactive gas in it at low pressure. There are two electrodes in there too, at several hundreds of volts between them, with the walls of the tube being the cathode and the wire in the middle being the anode. Imagine now that ionizing radiation hits the tube, then there some of the gas molecules will be ionized. The resulting ions will either reach the wire or the wall, thus we can measure them being there. The radix sonde is one thing, but what if we were interested in, electric charge in clouds? That's a bit specific, yes, but, well, you'll see in a second. There's electric charge in all clouds, storm clouds or not. See, cosmic radiation ionizes water droplets in the air, as in cloud droplets. This electrification isn't large, so we're not talking storm clouds now. This means that we can put a so-called electrode in the air, under the balloon and into the cloud that is, and have it collect whatever electric charge it can find and have it be fed into a capacitor. There's also aerosol counters of different kinds, depending on the aerosol that is. What? Aerosols are anything in the air which is small enough to float. That's what aerosols are. But they're not small enough to be a quantum thing. Bacteria, pollen, smog, that sort of thing. Or you could measure the Earth radiating out the energy it got from the sun by means of IR cameras, or its albedo, which is kind of the same but really isn't. There's loads of other stuff one could do, and we do all these things. Be sure of that. Balloons are just cool like that. In their serene, floaty, chill kind of way. They collect data, day in, day out, sometimes for a month or two, until they pop or are being made to pop. What's not to like about that in this hectic world of ours? Thanks for staying with me to the end. Join me on socials and YouTube, or check out kindnessthrough knowledge.com to book a presentation. See you next time.